Hey there. Have you ever stared at a bunch of chemicals on a page and felt like you needed a crystal ball to figure out what happens next? Well, today, we're going to trade that crystal ball for a chemist toolkit. Seriously, by the time we're done here, you'll have a clear, logical way to solve these puzzles. No magic required. Let's get into it.
So you see something like this, tin chloride plus nitric acid, and your brain just kind of goes blank. What's it going to make? It's so easy to feel lost here. But I promise you, the answer isn't just about memorizing a million different reactions. There's a real logic to it.
I'm serious. There is absolutely no magic involved here. Predicting reactions is all about having the right method, the right approach. Think of it like we're building a toolkit together. And once you have these tools, you'll be able to tackle these problems with way more confidence.
So here's our game plan. First, we'll talk about the problem itself. Then, we're going to build that toolkit with 3 key tools. Redox reactions, which are like a chemical battle, acid-base reactions, more of a simple swap, and precipitation, a solubility test. Then we'll put it all together into one awesome strategy.
Okay, our first tool is all about spotting what we call redox reactions. The best way to think about these is like a chemical tug-of-war. It's a total power struggle where substances are fighting over electrons. And the winner? Well, it's decided by which one has a stronger will to react, and we can actually put a number on that will. It's called redox potential.
All right, let's circle back to that first puzzle. To make things a little easier, we can kind of ignore the chloride for now, and just zoom in on the main characters. The tin ion, that's SN2+, and the nitric acid, HNO3. These are the 2 competitors in our tug-of-war.
So how do we measure their strength? With this number. The standard redox potential for nitric acid is 0.957 volts. Just think of that as its power score in this chemical fight. The higher the number, the stronger the pull.
And what about tin? Well, its redox potential is way lower. It's sitting at just 0.151 volts. So now we have our 2 fighters, and we know their power levels. Who do you think is going to win this battle for electrons?
And this is where it all clicks. Since nitric acid's potential, that 0.957 volts, is so much higher than tin's 0.151, it just wins. It's the stronger chemical, which means it has the power to basically force the tin into a reaction. It's really that simple. Higher potential wins the battle.
And because it's stronger, the nitric acid successfully oxidizes the tin. What does that mean? It rips away 2 more electrons from it, changing it from a tin 2+ ion into a tin 4+ ion. And just like that, by comparing 2 numbers, we've figured out what's going to happen. You know, this exact principle is what powers every single battery you use, a substance with a higher potential forcing electrons to get a move on.
Now, not every reaction is some aggressive tug-of-war. Our next tool helps us spot something much simpler, an acid-base reaction. You can think of this less like a fight and more like, well, like ions just changing partners. It's a really clean and predictable exchange.
Let's take a super classic example. Sodium hydroxide, which is a base, reacting with hydrochloric acid, an acid. We can imagine them as 2 couples out on the dance floor. You've got sodium with hydroxide, and you've got hydrogen with chloride.
So when they react, what do? They just swap partners. The sodium ion pairs up with the chloride ion, and that makes sodium chloride. Yep, that's just table salt. And the hydrogen ion gets together with the hydroxide ion to form H2O, also known as water. This simple swap is exactly what's happening when you take an antacid for heartburn. A base is just neutralizing that stomach acid.
Okay, our third and final tool also involves a partner swap, but this one has a really cool twist. Sometimes, when these new pairs form, one of them is completely insoluble in water. It just can't stay dissolved, so it literally crashes out of the solution and forms a solid. We call that a precipitate. Let's see how to predict it.
So check this out. We mix potassium chloride and silver nitrate together in water. Both of them dissolve just fine. Now, if we follow our partner swap rule, the potassium could team up with a nitrate and the silver could team up with a chloride. That gives us 2 brand new potential products.
So here's the big question, right? How in the world do we know which one is going to form the solid? Is it going to be the silver chloride, AgCl, or the potassium nitrate, KNO3? We can't just guess. We need some actual data to figure this out.
And that data is right here. The key is this thing called KSP, the solubility product constant. Just think of it as a solubility score. You can see for potassium nitrate, it's just listed as soluble. Its score is really high. But then look at silver chloride. Its KSP is a tiny number, 1.8 times 10 to the negative 10th power. An unbelievably small number like that is a dead giveaway that it is extremely insoluble.
And boom, that's our answer. The substance with that super low solubility score is our precipitate. In this case, it's the silver chloride. And this isn't just a neat trick. This is a core technique used in things like water treatment, where they use precipitation to pull unwanted stuff out of our drinking water.
And just like that, our toolkit is complete. We've covered the 3 main types of reactions you're going to see, so now let's put it all together into a simple 3-step strategy you can use for pretty much any chemical puzzle that gets thrown your way.
Okay, this is your game plan. From now on, whenever you see a reaction, first check for redox. Is this a power struggle? If it is, compare the potentials. If not, no big deal, move to step 2. Is it an acid-base reaction? Is it just a simple partner swap? And if you're mixing 2 solutions of ions, move on to step 3. Check for a precipitate. Just look up the KSPS values. This little process of elimination turns chemical guesswork into a clear, logical method.
You know, this all reminds me of a great quote from the brilliant scientist Michael Faraday. He said that chemistry is an experimental science. Our conclusions have to be drawn from data, from facts. And that's exactly what we did. We didn't just guess. We looked at the data, the redox potentials, the KSP values, and we let those facts guide us to the right answer.
So there you have it. You're armed with your new toolkit. You no longer have to just stare at an equation and wonder what's going to happen. You have a method. You can predict the future, chemically speaking anyway. So the only question left is, what puzzles are you going to solve first? Thanks for joining me.